Okay, the key to understanding the periodic trends of atomic size and ionization energy, and those two trends are, as we move left to right across the table, the size of atoms decreases. As we move down any particular group, the size increases. We see for ionization energy that as we go left to right across the table, ionization energy increases, so it gets progressively harder to remove an electron from an atom as we go left to right across the table. As we move down any group, it becomes easier to remove an electron. And what I want to do in this video is provide an explanation as to why these two trends happen the way they do. Now, on the right side of my screen, I have produced a diagram that relates a number of factors that the viewer needs to understand. All right. So in the nucleus of the atom is where we have our protons, and the protons have positive charges. The positive charge, all right, is instrumental in attracting the negatively charged electrons, and I'm depicting that relationship right here, all right, in a simple way. So we have a positively charged proton attracting a negatively charged electron, and they form a bonding interaction because these two opposite charged particles attract one another. All right, now in the diagram I show the energy levels that we have in the atom, where N1 is the energy level that is closest to where the protons are. We say that this energy level is lowest in energy, and when we use that term we mean lowest in potential energy. An electron that is in N1 is closest to the protons, so that electron is being attracted with the maximum amount of force. And as we move into higher energy levels, those electrons are being placed further and further and further away from where the protons are. So the potential energy of those electrons is increasing as we move away from the protons. Now, as the electrons are being added into higher and higher energy levels, their potential energy is going up, which means that it's easier to remove an electron from an energy level that is a long distance away from the protons than it is to remove an electron that is closer to where the protons are. So it's easier to remove an electron, say, from N7 than it is to remove an electron from N1. All right, now let's bring this back to the point of the video. So what I'm showing on the screen here are the period 2 elements, starting with lithium and going to neon. Now, it's important that the viewer have a basic understanding of electron configuration. So lithium, for example, has 3 total electrons. So if I was to write the electron configuration for lithium, it would be 1s2, 2s1. So as we go across period number 2, all these elements have already got a completely full energy level 1. That means, coming back over here to my diagram, that these elements already have filled energy level 1. And I'll just put the 2 electrons in this, which means as we go across period number 2, that we're actually filling energy level 2. All right, I'm going to put a circle around that. This is the energy level that we're filling as we go across energy level 2. Period 2, as we go from lithium to neon, we're going to be filling energy level 2. So I'm going to put a line under that here. The green represents the electron configuration of lithium. Now, as we go across, there's 2 main factors here that we got to pay attention to. All right, and Coulomb's law says that the force of attraction is going to be equal to, and this is the simplest form of this law, it's going to be equal to the product of the 2 charges, the charges coming from the protons and the charge coming from the electrons, and this is divided by the distance squared. This is force of attraction, all right? How hard those electrons are being pulled towards the nucleus. So as we go left to right, let's see what's going on with the force of attraction. And we can get a handle on that by calculating a value that's called Z effective. This is the effective nuclear charge. So we're calculating how big this positive charge is as we go left to right across the periodic table. All right, and Z effective is calculated very easily by the number of protons for the atom minus what we call the core charge, core electron charge. Now the core charge is not that complicated to understand. If we go back to lithium and very quickly we do its electron configuration, 1s2, 2s1. The 2s1 electron, this is the valence electron of lithium. So this is the outermost electron found in lithium. So coming back over here to my schematic, see, we already have 2 electrons in N1 for lithium. Those electrons are right here. These are the electrons in N1. And this electron is sitting up here in energy level 2. So it's a little bit further away from these protons. So these electrons right here are the core electrons. And they are screening the amount of positive charge. We have positive 3 charge here in the nucleus of the lithium atom, and these 2 electrons that are sitting in energy level 1 are screening this electron away from this charge. They're in between, they're in the way. So if we come back over here to my diagram, those 3 protons are sitting here, and the 2 electrons that are sitting in N1 screen this charge from the electron that is sitting in the outer shell of lithium. And we can calculate the Z effective, the amount of charge that this electron here actually sees or feels when it's sitting out here with these 2 electrons in N1 that are sitting between this electron and where those protons are, by subtracting from the proton charge the core electrons. So the amount of charge that's available to lithium's outer shell electron is +1. Now, we can do a similar calculation. I'm going to let the viewer do that for all of the atoms that are in period 2. And when you do that, here's what happens. Lithium is +1, outer shell. This is the effective nuclear charge that the outer shell electron is seeing. Beryllium is +2. Boron is +3. Carbon is +4. Nitrogen +5. Oxygen +6. Fluorine +7, and neon is +8. So you can see that what's happening as we go left to right across a period in the periodic table, that the nuclear charge, this effective nuclear charge, is increasing. It's going up dramatically. We go from +1 to +8 as we cruise across period number 2. It's going up. By the same token, what's going on with the distance? All right, now look carefully at the electron configuration, because as we go from lithium to neon, the electrons are being added into energy level 2. So coming back over to my diagram, as we walk from lithium to neon, we're adding electrons solely into energy level 2. Okay, and so from boron to neon, every single one of those electrons is been added to the 2p shell, which has the same distance from the protons as any subsequent electron was added. So the distance factor here is changing only to a small extent. All right, you might even argue, you can argue, and this is not absolutely truthful, but you can argue that the change in distance is about 0. So think about what's going on here. All right, the force of attraction is increasing dramatically as we go left to right across the table. The force of attraction for those outer electrons being attracted to the protons, because the nuclear charge is going up, the distance isn't really changing. And so your atomic size decreases because the electrons are being sucked in closer to the protons, and your ionization energy is going up. It has to as we go left to right across the table. Because the force of attraction on those electrons is increasing. So the amount of attraction that those electrons are being pulled towards the nucleus is going up.